Hello everyone. My name is Jake Robertson. I'm a master's student at the University of Freiburg, and today I'm going to be giving a really quick talk about our workshop paper at the AUTOML conference, FairPFN Transformers Can Do Counterfactual Fairness. Before I go any further, I would like to acknowledge our co-authors, Noah, Noor, and Frank, and also give a big shout out to the organizers of the AUTOML conference 2024. Right, so let's get started. Counterfactual fairness, and a counterfactual, is a question of what would have happened under different circumstances. And in the context of algorithmic bias and fairness, counterfactual fairness means that individuals receive the same outcome in the real world as in a hypothetical counterfactual world where they belong to a different demographic group. And this came from the original definition in the Kusner paper in 2017. Now, from a causal perspective, counterfactual fairness essentially means that when you intervene on the protected attribute, the outcome should remain the same, right? So this accounts for both the direct and indirect effect of discrimination. In practice, there are three ways of achieving counterfactual fairness, which basically boil down to fitting a predictor to causally fair variables, whether they just exist or you have to infer them. And as you can see, counterfactual fairness is a really intuitive, human-in-the-loop, individual level, and causal fairness criteria, also with a really strong analogy to legal specifications. However, it assumes that you actually know the correct causal model. And a lot of people, including a review by Casanova in 2023, argue that this is a really idealized assumption, especially in the face of these complex social science problems. Not only that, practitioners risk fair washing by proposing the wrong causal model, which can have adverse impacts, as shown in a study by Ma and colleagues in 2023. So the research question of this paper is, can we apply PFNs, which is a new and emerging machine learning technology, to learn to make counterfactually fair predictions directly from observational data, so removing the requirement of knowing the causal model. So to do this, we built off of TabPFN. And the main difference between our work is our fairness prior, where we model protected attributes, so things like sex or ethnicity, as binary exogenous variables in the structural causal models that we use to generate our synthetic pre-training data. And when we train our transformer, or when we pre-train our transformer, we do a pretty cool trick. And what we do is we essentially create two different data sets. We create a biased data set and a fair data set. So the fair data set is done by essentially removing the outgoing edges from the protected attribute in the data generating SCM. Then we pass in the biased data to the transformer. This is what it expects to see in the real world. And then when we calculate the loss, the transformer makes a prediction, y hat, and then we calculate the loss with respect to the fair y's, so the fair outcomes, which don't have the causal effect of the protected attribute. And in our study, we got really promising results. So we proposed a synthetic benchmark of different causal scenarios so that we could really be sure that FairPFN was doing what we wanted it to do. And in these studies, we saw that FairPFN achieves Pareto optimality in most cases, which shows that it's essentially able to identify and remove the causal effect of the protected attribute while maintaining a pretty high level of accuracy. We also tested directly for counterfactual fairness, and we saw on a real-world problem, the law school admissions problem, that FairPFN learns to align counterfactual and real predictive distributions. So we're really excited about this work, FairPFN, and there are a lot of really exciting directions. These include causal machine learning, fairness preprocessing, multi-objective. So we really encourage you to check out the paper and come speak to us at the conference. Thank you very much.